Okay, let's get started, please. Okay, so today we're going to be talking about differentiation. As I said in one of the earlier videos, a lot of this class is sort of going back through calculus and doing it the right way, like doing it the mathematician's way. Okay, so chapter 5, differentiation. Okay, so somebody tell me what it means to be differentiable at a point. So you've got this function, you have some function on an interval, say it's a real valued function, so we're looking at real valued functions here. You have some function here, and here's this point x. What does it mean to be differentiable at x? Just give me your calculus definition, if you remember. Anybody remember what it means to be differentiable?
You take like a point from the left side, and you take the slope from that point to the point you're interested in,
okay.
x, and then bring that point closer to x, and you hold the limit on the left side and right side, the slope is equal.
Okay, great. So you look at, you take some second point, and it could be left or right. Okay, let's call that point t, right? And you look at the slope of the secant line, right? You look at the slope of the secant line. You look at the slope of the secant line here, right? From between those 2 points, right? So you look at f of t minus f of x, t minus x, and then you take the limit as t approaches x, right? So that could be from the right-hand side or from the left-hand side, doesn't matter. And if that thing actually converges to something, then you call that value the derivative, right? Right? You call that value the derivative. You know, it is sort of pictorially, it would be the slope of the tangent line, right? The slope, if you took the slope just at that one point, right? Right. So if this limit exists, right? So if the limit exists, we call it f prime x and say f is differentiable at x. Right. Okay. So that's your old calculus definition, and it's actually our definition here. So that's going to be our definition as well. I guess the only thing is that now we really know what the limit means in a much better sense than you did before. Okay. Okay. It will be profitable, say, to think of f prime in the following manner. Okay, so I'm going to take this definition that you know, and I'm going to change it just a little bit. Okay, so if I say that the limit of f of t minus f of x over x minus t as t approaches x equals some value, right? Then that's the same thing as, I might as well say that. So here I'm saying that there's some number f prime of x such that this is true, right? That's what being differentiable means, right? That there's some number and this limit equals that number. Okay, right? That's what differentiable means. I'm going to just change that a tiny bit and write it like this. That there's some number such that this minus that number equals 0. Okay, I think nobody will object to that. Right? Right, that's exactly the same thing. Okay? Now I'm just going to put in some notation. I'm going to call this thing u of t. Okay, so u of t, if you think about it on the picture, this is the difference between the tangent, the slope of the tangent line, and the slope of your secant line. Okay, so you've got your secant line passing through the second point at t, right? You've got your secant line passing through the x point and the t point. That's this thing. The slope is this, and you look at the difference. So this is some sort of like how close you are to the actual derivative. Okay, so let's call that thing u of t, and I'm going to rewrite the definition like this. So this is the same thing as saying that there exists a number f prime x, right? There exists a number f prime x and a function u of t such that f of t minus f of x over x minus t equals f prime of x plus u of t. And u of t, as t goes to x, u of t goes to 0. Yeah, Andres.
Is it x minus t or t minus x?
Oh, sorry, t minus x, thanks. Okay, is that all right? Does everybody see that that's exactly the same thing as I'm writing here? So being differentiable means that there's this number and there's this u of t. You see what u of t is? U of t is this thing over here, right? U of t is actually the difference between this and that, right? So there's, this adding in this u of t isn't really saying anything more. Okay, so there exists this number f prime and this u of t, which is defined in this way, where the limit of u of t is 0. Right? It's exactly the same thing. Okay. So now I'm going to rewrite it. I'm going to change it a little bit more. So there exists a number. There exists f prime in R and a u of t. U of t such that f of t equals f of x plus f prime x t minus x plus u of t minus x, and the limit of u of t is 0 as t approaches x. Okay, so all I did here was I just multiplied through, I wrote the same thing, it's just that I multiplied this out. I multiplied both sides by t minus x, and then I moved the f of x to the other side. Okay, so if you agree with this one, you should agree with this one, as long as you believe in elementary fractions. Right? I trust you do. Okay? But this is great. Now, so we've taken our definition and we rearranged it, and now it looks like it's a kind of different statement. It's actually the same statement, right? It's actually the same statement, but it has now sort of a different interpretation. Okay, so let's think about what differentiable means now. Okay, different perspective on what differentiable means. Differentiable means that your function, so differentiable, so this is differentiable at x, right? Differentiable at x. Okay. Differentiable at x means that your function can be expressed as f of x plus f prime x t minus x plus u of t t minus x as this thing goes to 0. And this thing goes to 0. But let's look at this thing. What is this thing? What's this thing here? Right? As a function, if I write this thing as L of t, as L of t is f of x plus f prime x t minus x. Anybody see it? Go.
I see a linear line.
It's a line, right? It's a line. What's its value at x? Well, at x, the value is going to be f of x, Josh?
It looks kind of like the first order Taylor series.
The what?
I think a first order Taylor series centered around X.
It is a first order Taylor series, aka the tangent line. Okay, yeah. So you've got this line. Yes, exactly. Very good. Very good.
Oh, man.
Yes. It is indeed. Okay, so right, it's a linear function, right? And you notice that at time when t is x, you get f of x. So it passes through this point, right? It passes through this point x comma f of x, and you notice that the slope of the line is f prime, right? The slope of the line, like, differentiate this with respect to, the slope of the line is right here, right? The slope of the line is f prime, right? So it's got the slope of that it passes through that point, and it's got the slope of the tangent line. It is the tangent line. Okay. Okay. So what is differentiable? Let's go back to thinking about what differentiable actually means. Okay. What does differentiable mean? Differentiable means that your function is basically a tangent line. Differentiable at x means that your function is basically a tangent line plus some sort of thing that vanishes as you go close to x. Right? So as t goes to x, this thing goes to 0. In fact, it goes to 0 in a very fast way. Right? This part not only goes to 0, but this thing also goes to 0. Right? In a linear way. So even if I divided, so this you can think of as some sort of this product here you can think of as some sort of error. Okay? So your function is differentiable if it's the tangent line plus an error that goes to 0 even when you divide it by t minus x. That's exactly what differentiation is. Differentiability at x is. Okay. Your function is differentiable means that your function can be approximated by the tangent line with an error that shrinks very fast in the sense that even if you divide this thing by t minus x, it'll still go to 0 as t goes to x. Okay. So that's what's actually in this, that's what's encoded in this definition, but maybe we needed to expand it out a little bit to make it clear what differentiability means. Okay. Okay. Any questions? Okay. So from here, so that's how we're going to think about differentiability. That means that your function is approximable by the tangent line in this sense, with an error in that sense. Yes, don't.
So it's that error when difference has epsilon, and so there's like a neighborhood around like x, that's like within like f of x plus epsilon.
Say it one more time.
Like can we write this as like an epsilon delta type e? Like we say like there's a neighborhood around x such that like it's within the error.
Yeah, you could use this as an approximation sort of thing. So like here's your function, here's your tangent line, right? Here's your tangent line, and you know that for one thing you know that this whole thing goes to 0. Right, because this goes to 0 and this goes to 0. So definitely the product goes to 0. Okay, so one thing you could say is that I can trap my function. No, you know that. Let me say it this way. You know that the u of t goes to 0, right? So if you trap your u, if you say, okay, I know that my u of t is smaller than some epsilon. Okay, what's that? Then you've got this thing over here is basically trapped between a line of positive slope epsilon and negative slope negative epsilon. Right? So, right, because this u of t is smaller than epsilon in absolute value. Right? So you could say, okay, I know that I can trap this between a line of positive, so between my tangent line plus a line of positive epsilon slope and negative epsilon slope. right? So that's what this is saying, right? That's one way you can think about this, right? That you can, for any epsilon you choose, you can find a neighborhood in which your function, you can find it, so for any epsilon you choose, you can find a neighborhood in which your function, this guy, is trapped between the tangent line plus a line of slope positive epsilon and a line of negative epsilon. Okay, so your function is going to be trapped between a sort of like bow tie, I think. Okay, yeah, thanks for saying that. Okay, let's go on. From there, okay, so then we're gonna, prove sort of the standard, properties of differentiation, properties of differentiable functions, properties of differentiable functions. So one in particular, right? If f is differentiable at x, then it's continuous at x. Okay. So I should have kept the picture up that we just drew, right? You know that your function, so here's my function, here's my tangent line, right? And you know what continuity means, right? Continuity means that to show continuity, we need to show that the limit of f of t as t approaches x is f of x, right? That's continuity. So we want to show that the limit actually attains that value, right? So here's x, here's f of x. We want to show that the limit actually attains that value, right? So one way we could do it is basically by using, pictorially it's kind of obvious, right? Because you know that you can trap the function between this bow tie thing on it, right? And you know that the top of the bow tie and the bottom of the bow tie both go to f of x, right? So the function being trapped between them is going to go to f of x also, right? So that's sort of the intuitive way of going off of thinking of this as the tangent line thing. That's how you could think of it. It's maybe even more straightforward to just use this fact here. So you say, well, look, right? We want to show that the limit of f of t as t approaches x is f of x, right? But we know, since f is differentiable, we know that f of x equals, f of t equals f of x plus f prime x t minus x plus u t x minus t minus x again, where the limit of u of t is 0 as t goes to x. Right? Well, what happens, so if we take the limit of, as t goes to x on both sides, what happens? The limit of f of t is going to be what? What's going to happen over here? Well, f of x, it's not going to move, right? Because t is moving. F of x doesn't have any dependence on t. What happens here?
0.
You get 0, right? Because this is a constant times something that goes to 0. So it's f of x plus 0. What happens to this thing? Also 0, right? Because this thing goes to 0 and this thing goes to 0. So 0 squared, right? Okay. Right. So you get f of x. Okay. So this is, I think I like this way of thinking about continuity, right? I know that it's probably true. You probably did it in your calculus class. You probably said, well, f prime x equals the limit of f of t minus f of x over t minus x as t approaches x. And then you did something like you multiplied both sides by the limit of t minus x as t approaches x. So this is what you might see in a calculus class. You multiply both sides by this limit. Multiply both sides by this limit, right? And then combine these things together and say, oh look, this limit is 0. Right? That the limit of f of t minus f of x as t goes to x is 0. Right? So that would also show it. I find this proof far more opaque. It doesn't really tell you what's going on. So anyway, this is like the calculus proof. Okay. Let me not waste any more time on that. Okay. Okay. So yeah. So differentiability implies continuity. Other basic properties are things like there's differentiability and arithmetic. Right, that if you take the derivative of a sum, then you get the sum of the derivatives. Right, if you take the derivative of a product, then you do not get the product of the derivatives. You take the derivative of a quotient, then you get, whatever. Right? You've seen all these things since you were younger. Okay. So, I think it's useful to do at least one of these as an example. So let's take the second one, because it involves a sort of philosophy. Okay, so let's do the second one. Okay, so right, we want to show that the derivative of the product is this sort of thing, right? And so let's look at right. We want to show that the limit of f times g of x of t minus f times g of x over f times g over t minus x as t equals x equals this sort of thing. Okay, that's of course what we want to show. Right? So let's look at it. So consider, let's consider that the thing we're taking the limit of on the left-hand side. So we have f of t, g of t, minus f of x, g of x, over t minus x. Okay? Okay. So, right, so just as a game, you're trying to slide in, you're trying to fit in here the derivative of f, right? So what we'll do is say, okay, let's put in, let's go like this. Let's play the following game. We're going to subtract off f of t g of x. And then we're going to add it right back in. Okay. Everything over t minus x. Okay? So we added in a clever looking 0. Okay? We added in a clever looking 0. This is kind of a useful trick because what we're trying to do here is slide in the derivative of a g. Okay? So look, if I put this thing in here, then you notice that I'm putting a derivative of g in here. Right? I've got a g of t minus a g of x over t minus x. Okay. So by putting in this term, it allows me to factor out a derivative of g here. Okay. So let's write this out here. This is f of t times g of t minus g of x over t of x, and then we have this other thing here. We have a g of x here, and we have an f of t minus f of x over t minus x. Okay, so this was, this is something that happens a lot. You introduce some terms by adding them in a way, by using a cleverly chosen 0. Okay, so this is like a cleverly chosen 0. Is slid into your thing so that you have things that you recognize, and then you can factor them out. Okay, right? So then when you take the limit, so then let's take the limit as t goes to x. Right? The limit t goes to x. Limit as t goes to x. You see what happens, right? This thing is going to turn into this thing turns into g prime x. Right? This is g of x. This turns into g of x, f prime x, right? And then here I get the limit of f of t as t goes to x, and that's going to be f of x, right? Right? Why is that f of x? How do I know that that's f of x? As t goes to x, limit of f of t as t goes to x. Okay, we just proved that it was continuous, right? We just proved that the function being is, right? We assume that we need to assume that f and g are differentiable at x, right? For any of this to make sense, right? So being differentiable this guy is continuous, and so that works out. Okay, everybody all right with that? Any questions? Maybe. Should I go faster? Close your eyes for a second. Should I go faster? Raise a finger if I should go faster. Okay, raise a finger if I should go slower. Okay. Most people are content. Okay, so let me make one comment that, in fact, we could prove this using the tangent line interpretation. Okay, that is, you could show that that the product is going to be approximated by the appropriate tangent line plus some error that goes to 0 in the right way. Okay, so you could do it that way. It's maybe a good exercise for you to try, but it's kind of uglier. So I wanted to do things this way. Okay. The next theorem we're going to do, the chain rule, we will prove using the tangent line approximation. So that'll maybe serve as a model for you. Okay, so the chain rule, right? So Okay, so the setting looks like this, right? You have some function, it's a continuous function. You have some other guy on some interval I, where the interval where I contains the image of f. Okay. If f is differentiable at some point x in AB, and g is differentiable at f of x, then, as you know, the composition is differentiable at x with the derivative being the derivative of g valued at f of x times f prime x. Right? So just so you know, of course. Right? I'm sure you're very familiar with this statement. Okay. Okay, but let's prove it. Let's prove it using the tangent line approximations. Okay, so here we go. We say, well, we want to show, what do we want to do, right? We want to show that that the limit of g of f of t minus g of f of x over t minus x as t goes to x is going to be g prime f of x, f prime x, right? That's what differentiation means. Okay. Okay. So now we're going to use the tangent line interpretation. Okay. The alternate interpretation of the derivative. See? So you say, well, let's look at the top, the numerator on the left-hand side here. Okay. Let's look at this thing. Okay. We know that that is going to be f of t minus f of x times g prime f of x minus some vanishing error v of f of t. Right? Is that clear? So we're using the tangent line approximation here. Right? Okay. Everybody okay with that? So, okay. And then we'll use the tangent line approximation. So that's using the tangent line approximation of g, and then we'll do the tangent line approximation of f. Okay. So we say, okay, now let's take this guy and write it in terms of the tangent line. Well, this is going to be t minus x times f prime of x plus u of t. I'm sorry. Let me make this a plus. It doesn't matter, but I'm going to make this a plus. G prime of f of x plus mu f of t. Okay, is this making sense? I hope this is making sense. Anybody have questions? Yes, Keisha.
You start with the limit.
Say it again.
You start the limit as t approaches x all the time.
Say it one more time.
You start the limit.
I still have the limit. Yes, I haven't taken it yet. Yeah. Okay. So now I'm gonna divide both sides by t minus x, right? So then g of f of t minus g of f of x over t minus x equals this product over here, f prime of x plus u of t, g prime f of x plus nu of f of t. Okay, and then you take the limit as t approaches x, and you see what happens. Right? What happens? Well, this u of t is going to go to 0, right? U of t goes to 0, right? And f of t, by continuity, f of t is going to go to f of x, right? Because f, remember, f was continuous, right? So, right, and also differentiable at x. So this is going to go to f of x. Well, you know, right, and yeah, as that goes to f of x, then nu of t is going to go to 0, right? Because g was differentiable at f of x, right? So its error goes to 0 as this term goes to f of x. Okay. So you end up with f prime x, g prime f of x. Who has a question? Yes?
I was just wondering, what is the mu there for? I don't get it.
What's the nu?
Yeah.
This nu is the error for g prime,
Okay.
right? So remember our function. So g is differentiable. G is differentiable at f of x, right? So we know that that the function near f of x is approximable by the tangent line plus some error, right? This is the error. This is the error for that guy. Okay, everybody all right? Everybody all right? Okay. Okay. So that's the proof of the chain rule. Okay, so the next thing we're going to do is get on to the other the other important results about differentiable functions in calculus. So that is, we're going to head for the mean value theorem. So this is maybe the most important theorem in differential calculus. Okay. So let me erase everything here. Okay, so yeah, so like I said before, there's a lot of things that are, there's a lot of important theorems, like the most important theorems in calculus are generally not proven, and so we're gonna prove them now. Okay, so I'm sure you've seen some of these things before, but you probably haven't seen their proofs before. So, okay, so just to be proper here, let me put up some definitions. So you have a function. So x is a metric space. And you have a function on that metric space, and you have a point in the metric space. Okay. So if there exists a neighborhood n delta of p, such that f of q is less than or equal to f of p for all q in that neighborhood, then we say f has a local max at p. Okay, and similarly local min, right? So this is just you've seen this before, right? You have some point P, and it may not be the highest value, but there's a neighborhood in which it is the highest value, right? So there's some neighborhood, some delta neighborhood, right? There's some neighborhood, and f of P is the greatest value in that neighborhood. Okay, then you say f has a local max there. Or f has a local min there. Okay. Then kind of the standard theorem that follows this is sometimes called Fermat's theorem, or maybe the critical point theorem. That says that if f prime of x exists, and f has a local max, f has a local max at x, then the derivative must be 0. Okay, I'm sure you've seen this sort of thing before, right? If we wanted to prove it, you could prove it using the picture that we had up earlier. So you could prove by picture. Suppose your derivative were greater than 0. Suppose your derivative were greater than 0, right? That would say that your tangent line, so let's say that this is x, here's f of x, okay. That would tell you that your tangent line has a positive slope, right? And then you could say, well, now let me get close enough that my u is in absolute value smaller than, say, half of that slope. Right? Right, so pictorially you say, well, I can get close enough that the slope of that I can trap this guy between two functions where the slope of the lower guy is still positive, right? The slope of the lower guy, right? My slope is not gonna get to 0, right? That means that my function will be trapped inside here, but that means that my function is going to be higher on, bigger on the right side and lower on the left side, right? So that would tell me that x is not a local max. If you wanted to prove it using the alternate definition. Okay, are you guys getting this? Yeah, okay. Okay, so now we're going to go through a sequence of theorems that build up to the mean value theorem. One of them will be something called Cauchy's generalized mean value theorem, which you need to prove L'Hopital's rule. So here we go. Okay, so here's a bunch of theorems that I'm sure you've seen before. First is Rolle's theorem. Okay. Somebody tell me what Rolle's theorem says. What's Rolle's theorem? Anybody remember? Anybody? You saw it, you forgot it, didn't like it. Someone, go ahead.
Is it that given any interval a b where a function is differentiable on a b, there's a point c such that f prime of c equals f of b minus f of a?
You're sort of saying the mean value theorem, which is like even better than Rolle's theorem. But Mo, go ahead.
So on the interval AB, if f of a equals f of b, then there's a spot c in which f of c equals 0. F prime of c equals 0.
Very good, very good. Okay, great. So, right, so the picture is you've got two dots, right, and you've got your function that goes like this, and you know that at some point, so there's a and b, there's going to be some point where the function has a slope of 0, right? That's Rolle's theorem. So let me write it down. Normally, we have some function on AB, and it's continuous, right? And it's differentiable on the interior if f of a equals f of b, then there exists a point C between the a and b where f prime of c equals 0. Okay? Okay, now the proof of this actually involves the extreme value theorem. Okay, what does the extreme value theorem say? Anybody remember? Yes, James.
I think the finite related being function will achieve a maximum or relative local maximum.
That's right, that's right. So says that if you have a continuous function, if you have a function that's continuous, then it attains a max on AB and attains a min on AB. Right? There's some point where a max is attained and some point where a min is attained. And you remember that this is actually because of the functions continuous on compact sets have compact images. Okay, so this is something we actually needed to use the notion of compactness to get. So again, this is something that you couldn't get in normal calculus. Okay, so you know that there's some places, so there are two places, one where a max is attained and one where a min is attained. Okay, so case one, suppose those both occur at the endpoints. Okay, suppose they both occur at the endpoints. In that case, what's going to happen? So you got your function, the max and the min occur at the endpoints. It's a flat line, right? Because the function was equal at the endpoints, right? So it's going to be flat. Okay. In that case, we're done. Definitely, there's a place where the derivative is 0, right? Right. Done. So f is constant. This triple bar means f is constantly equal to some constant. Okay. So f is constant. Okay. Case 2, suppose one of them occurs in the interval AB, in the open interval AB. Like, suppose there's a max. Suppose a max occurs in the middle someplace. Well, then by the previous theorem, right, the critical point theorem that we just said, the derivative is going to be 0 there. Right, so by the previous theorem, f prime prime equals 0 here. Okay. So that's the proof of Rolle's theorem. Okay. Let me put up a corollary. Suppose you have two functions, f and g, on AB, both continuous and they're both differentiable on the interior AB. Suppose now that f of b minus f of a equals g of b minus g of a. Okay, so the picture is, here's A and B, right? Here's f of B and f of A, and the difference between g of B and g of A are the same. So this is f of B, this is f of A. Suppose that difference equals that difference. Right? So g of B and g of A. Okay. Think about it for a minute and tell me what the conclusion is. Okay, I think a minute is up. Maybe it's not up. Turn to a neighbor and tell them what the conclusion should be. Okay, does anybody want to say what the answer is? Other than Dylan? Okay, go ahead, Dylan.
F minus g, the derivative has a derivative equals to 0 on the interval a and b. So you can rearrange it.
Yeah. So f minus. So if you look at the difference, right? If you look at the difference, you see. So f minus g. So then there exists a c in the interior where this is equal to 0. Right? That's what you're saying. In other words, where the derivatives of the functions are equal. Where f prime of c equals g prime of c. Okay. So just like the first statement, if you thought of it in terms of like a car on a linear track, right, meant that if your car starts in one point and ends up at that same point, then it must have a 0 velocity at some point. Right? This one is saying that if you've got two cars on tracks and the difference between their starting and end points are the same, there must be some time where their velocities were exactly the same. Okay, and the way you see it is, of course, by considering the difference. So consider the difference f of x minus g of x. Right. Right. Then d of b equals f of b minus g of b d of a equals f of a minus g of a. But you see that those are the same, right? If I move this to here and that to there, right, I get f of b minus g of b equals f of a minus g of a. Okay, so these things are equal. So d of b equals d of a. So, right, the distance at the end equals the distance at the beginning, right? And so there must be some point in the middle where the distance function has zero velocity. Well, d prime having 0 means that the difference that f prime equals g prime. Okay. Questions? Anybody? Okay. Okay. So that's sort of like a teaser to get us up to the main mean value theorem, which is called the generalized mean value theorem, or it's sometimes called Cauchy's mean value theorem, after the analyst who created this. Okay, so Cauchy's mean value theorem. So here, first we had some function that had to be equal at the endpoints. Then we had two functions whose differences had to be equal at the endpoints. And now Cauchy's theorem is just going to be about two functions in general. Okay, there's no constraint on it. So there's one function, and then there's another function. Okay, no constraint on what happens at the endpoints. Okay, and what can you say in that case? Okay, so Cauchy's theorem goes like this. Suppose you have f and g that are both on the same interval. They're continuous there. They're differentiable. They're differentiable on the interior, right? And that's it. In that case, then so in this case, when you have two functions that ended, that traveled the same distance over, then there was some point where the velocities were the same. Okay. This one has a kind of interesting statement. Let me write it like this. It says, then there exists a point where f prime c, no, I wrote it backwards. Doesn't matter, but f of b minus f of a g prime c equals g of b minus g of a f prime c. Okay, so if you have two arbitrary functions, no constraint on where they start and end, then you can still say something about it. And if you want to think about this physically, you can rearrange this a bit and say, I mean, assuming that I'm not going to divide by 0, assuming that the things I'm dividing by are not zeros. Okay, so the quotes are because some of these might be 0. In case they're not, in case they're not, and you can make a quotient like this, then this quotient would be true. And you see what it's saying. It's saying that given two arbitrary cars, no constraints on where they start and end, then you're always guaranteed a point where the ratio of their instantaneous velocities equals the ratio of their average velocities over the time interval. Okay, and yeah, it's this sort of statement. You can sort of see it it will lead us into L'Hopital's rule. Okay, something about the functions over here, something about the ratio of the functions over here, something about the ratio of the derivatives over here. This will actually give us the proof of L'Hopital's rule later. Okay. Okay. So let me give the proof of that. So proof. So I'm going to throw out the case. So if G of B minus G of A equals 0, then actually we're done by Rolle's theorem. Okay, right, because if G of B minus G of A equals 0, you know there's some point where G prime is 0. Right? And so you get, at that point, 0 equals 0, and you'd be done. Okay, so we don't have to worry about that. Let's not worry about that. So we assume G of B is not equal to G of A. Okay, so now we do something clever. We twist one of the functions. So multiply G by f of B minus f of A over G of B minus G of A. Okay, so let's call that alpha. Okay. So then you think, now let's consider the two new functions. So consider f and alpha G. Okay, f and alpha G. Well, f of B minus f of A. If I look at f of B minus f of A, and I look at alpha G of B minus alpha G of A, you guys see what happens, right? Right? Alpha is this thing. When I look at alpha G of B minus alpha G of A, that's of course the same as alpha G of B minus G of A. Right? But alpha times G of B minus G of A is f of B minus f of A. Right? So I scale the second function by this constant that makes it so that the new pair satisfies the conditions of the last corollary. Okay. So what does that tell me? That tells me that there's a place. So there exists a C where f prime C equals alpha G prime C. Right? But that's exactly what I wanted, right? Because then, right, so f prime C equals f of B times f of A over G of B times G of A times G prime C. And I can multiply both sides by the denominator here, and I get the relation I wanted. Okay. Everybody good? I hope you like that. That's kind of nice. Okay. Any questions? What's the mean value theorem? Anybody remember the plain old mean value theorem? Someone?
It's either on an interval AB where f is differentiable on AB, there's just a point C such that f of A minus f of B equals, or f of B minus f of a equals b minus a times f of c.
Right. So there's going to be some point where the instantaneous velocity equals the average velocity. Right? That's what the mean value theorem says. Right? Now the mean value theorem, as you might suspect, is an immediate consequence of the generalized mean value theorem. Right? If you take one of these functions to be the line, to be just the straight line, L of x equals x. Right? Suppose I let g of x be equal to x, right? Then you see that the standard mean value theorem just falls right out of this. Okay? Because, so, corollary, right, so notice if g of x equals x, we get that f of b minus f of a times 1 equals b minus a times f times c, right? So that gives me the mean value theorem. Okay. Okay. So I guess there are a couple other things that that follow from this. I will just prove one of them. So a couple usual consequences of the mean value theorem, right? If f is differentiable in some open interval AB, then say, if f prime is always non-negative, then you know that it's monotonically increasing. Right? If it's always equal to 0, then it's constant. Right? And if it's less than or equal to 0, then it's decreasing. Right? So maybe turn to somebody nearby and prove one of these things.
Rolle says that I think if you can do mean value, say there's not yeah, so mean value. Then you would say there's some
Okay, who would like to? Let's do this one. Maybe this one is the trickiest one. I don't know if anyway. Let's do the one where it's constant. Anybody want to talk about that one? If you know that the derivative is 0 everywhere, then your function is going to be constant. Yeah, someone.
So then we know by the mean value theorem that on the interval AB, f of b minus f of a equals b minus a times f of x for some x in the interval, and or f prime of x for some x in the interval. And if we know that f prime is 0 for all x, then we know that f of b minus f of a has to equal 0. Therefore, f of b equals f of a for any interval of ab.
Okay, okay. So I'm going to use x and y rather than a and b.
Okay.
So our function is defined on some open interval a, b. Let's take any 2 points x and y. Okay, right? So by the mean value theorem, you know that, so let's say that x is less than y. We know that there exists a point between x and y. So take any x and y in AB. By the mean value theorem, we know that there's some point between them where f of y minus f of x over y minus x equals f prime of c. Right? But f prime of c equals 0 by assumption. Right? So that tells you that f of y minus f of x is equal to 0. In other words, that f of y equals f of x. Right? So whatever 2 points you choose, they're going to have the same values. Right? Or, I mean, if you wanted, you could say, fix 1 point, x naught, and then let y move around. Right? Fix 1 point x naught, let y move around. All of those f of y's is going to be equal to x naught. Right? And so the function is constantly equal to that value at x naught. Okay. Okay, I was going to say something interesting, but I forgot what it was. Like, come on, end with something kind of interesting. But no, that's it. Okay, that's it for today. See you guys next time. Oh yeah, okay, here it is. Yes. Okay. So there are functions that are differentiable. So I think some of you heard of this function, the Cantor-Ternary function. If you haven't, look it up. The Cantor-Ternary function is differentiable almost everywhere. So in terms of time, you can think of it as it's differentiable except on what's called a set of measures 0. So in terms of time, you can think of it as being differentiable 100% of the time. Okay, there may be instance when it's not differentiable. Okay, but there may be instance where it's not differentiable, but there's no like interval on which it's not differentiable. Okay, so it's differentiable 100% of the time, but even so, and its derivative is 0 whenever that derivative is defined. However, it travels, so it actually increases. It's an increasing function, even though its derivative is 0 100% of the time. Okay, so something to look forward to. Okay, that's it.